Hi everybody, and welcome to Mike's Garage. I'm Mike, and welcome to my presentation of the moving magnet motor and a primary use for this design with demonstrations. Note 1 of this slide describes the input section to the motor. Note 2 of this slide describes the magnetic system used in the motor. And note 3 of this slide describes the output section of the motor. We'll start with an actual look at the motor, the design and build of the motor, the installation of the motor in a test fixture, installing that test fixture into a test enclosure, and then performing some operational tests. Now this is a prototype, so please excuse the crude construction, but it does work. This is a photograph of the actual armature, the moving magnet armature, and just briefly, I'll describe it for you. We have these black polycarbonate shafts on either end, and then there's a permeable steel pole piece at each end, followed by the two magnets, the two neodymium magnets, which are 3/4 in diameter and 3/4 long, and a center spacer that's also a permeable steel. And we use this to set the dimension of the travel of this armature based on how far we want the excursions to be. This is a photograph of a iron powder field assay of the magnetic fields surrounding the moving magnet armature. Notice in the center of the photograph, clusters of powdered iron gathering around the poles, the very poles, the north being on the left and the south being on the right. As we move out, the patterns go in an axial direction between the poles, giving it that curved section in the center. And as we move further toward the ends, the field patterns have turned radial. In other words, they're just about pointing in, and that's a function of the pole piece arrangement. It's important to note that the two strongest attributes of this design that contributes to the power handling, the sensitivity, and the efficiency of the design is the short flux path between the north and south pole and the strength of those neodymium magnets. And we'll show you next the coils that are going to produce the axial field around that when the motor is all assembled. This is a photograph of a couple of the prototype coil assemblies. The one on the right actually ran too hot, and so the one on the left has the 148 grams of copper wire in it and runs much cooler. In the one on the right, if you look toward the end that's most visible, you'll see that blue silicone bearing sitting in there. And here's just a different angle on the same two structures. Note that the coils are wrapped around that fiberglass tubing, 20 millimeter inside diameter, and notice that the spacing on the top set has been increased. The spacing of the coils gives us some isolation. If you refer back to that magnetic field pattern, you can see why that might be important. This is an old prototype drawing. You can disregard that cone on the left, it's changed. But what I'd like you to notice is the assembly of the motor. I've got the actual moving magnet armature above the drawing, and you can see that it's aligned with the moving magnet armature in the drawing, which is in the center of that fiberglass tube. And you can see the coils that we looked at, numbers 7 and 9, wrap around that like shown. And at the ends, Item number 6, where the left shaft comes out of the tubing, is the silicone bearing. And at the right end, again, where the shaft comes through, at the other end, the right end, we have another silicone bearing in there. So briefly, item number 12 is that permeable steel spacer. Items 11 and 13 are the neodymium magnets. Items 10 and 14 are the pull pieces, and the shafts, number 5, and the ones on either end can be any length you need, and are polycarbonate. Thought you might be interested in seeing what the assembly looked like. This was during fitting of the heat sinks, part of the process, of course. And this is the completed moving magnet motor. At the right end, you'll see that clamping collar. That's there as a counterweight since we had to reinforce the moving diaphragm that we're now using. You can see both of the coils that have been coated with a insulating varnish. The heat sinks have been fitted, and the connection in the center of the structure pretty much is the power in. The wooden structure at the left is glued to the fiberglass shaft, and this is what is clamped in the test fixture when we install the motor. On the left end, you see an aluminum clamping collar. That is actually sets the distance away from the moving diaphragm, in this case, that the motor will be located. And once we assemble it, we'll simply put another clamping collar on the other side, holding that diaphragm in place. At any rate, this is a picture of the complete design. All right, we're going to assemble the transducer now. Before you see the moving magnet motor that we described earlier. And just briefly, this is the mounting surface that we're going to use to connect the motor to the frame. I'll show you that. This is the driving end. This is where the impact drive to the diaphragm is attached. That's right here. Now we only have about a square inch of drive surface here, so we've installed these sorbethane dampers on there to help spread that force out, because the the diaphragm surface area is about 120 square inches. So we have 1 square inch here, 120 we're driving. So there's a lot of force concentrated right here. And these sorbethane washers help us sort of soften the blow, if you will, and keep everything nice and quiet. No mechanical noises and that sort of thing. And we have those sorbethane washers on either side of the diaphragm. So let's look at the diaphragm real quick. All right, our diaphragm is a flat foam board radiator, and we chose the flat surface because it reproduces the impact noise and sounds, of course, because of the high pressure peaks we really want to get out there. A typical cone, due to its shape, has a phase distortion in it that we've eliminated. This flat surface produces a constant phase throughout, but it's much harder to drive, and so we had to add these reinforcing rings. These are plywood with screws on both sides to spread that 120 to 120 square inches to 1 square inch force, which is concentrated right here at this point. So that's the moving diaphragm. This is the frame that we've chosen to build our prototype on. It's, as you can tell, it's a speaker frame where the large magnet's been removed and replaced with this wooden structure, which gives us place to mount the other wooden structure that holds the moving magnet motor in place. And this split here, when we get the motor in there, we'll tighten up this screw clamp here, and it'll close this gap, holding the motor in there real secure. So, and that works like this. Look from the, I hope you can see, but the motor will fit in there just like that. Give it a little jiggle to get it to fit nice in there. And then we're going to go ahead and tighten this screw clamp, keeping the motor in there nice and tight. So that's all there is to mounting the motor. Now we've got our motor in there nice and rigid. And so now we can put this like this. This will help us a little bit. Here's our sorbethane washer. Here's our moving diaphragm, which fits this frame just right. And the final piece is one more sorbethane washer on this side, a clamping collar, which is tightened, and now we have the complete assembly, which moves just like we want it. This plywood will be captured between the frame and the enclosure and keep everything nice and tight. But I think you can see the other clamping collar in there. And you can see that the motion is being transferred nicely. So anyway, that's the completed transducer right there. All right, here's a look at the test enclosure. What we've got here is about a 3-foot long, 8-sided box. It should be round, ideally. I'd rather not have these flat surfaces and these angles. But at any rate, on this front surface is where the transducer mounts, and the part that's facing the camera would be the impact surface. So the impact surface is facing us when the transducer is installed. Further down in here, we have a chamber that's about 3 cubic feet. And up in this corner, you see a slot that is the entrance to the air column. The air column wraps around, like I'm hoping you can see, all the way around, and exits out here at an exponential horn. Okay, that's the horn, and that's the relationship with the horn. And you can see I've got the horn pointing out to the left and down slightly, which suits this particular room that we're operating in. This is an outline of the test, the operational test we're going to perform. Starting with an acoustic target. The acoustic design range for this particular transducer is 27.5 hertz to 55 hertz. That's the key of A0, the leftmost key on the piano, to A1, 55 hertz. I'm not sure if you'll be able to hear anything, but that's where we're going to start. Finishing with impact target testing, which is really an excursion test. We're going to go down 3 more octaves from 27.5 hertz at A0 to 13.75 hertz at A-1, 6.875 hertz at A-2, and 3.43 hertz at A-3. This is an operational test only. I think you'll find it interesting. It's mounted to the test enclosure, which you saw in the previous clip. Down here we have our function generator. Right now we're set at a frequency of A3, 220 hertz. We have our 400 watt power amplifier right here, and we're going to be running most of these tests at a minus 20 dB, which is roughly the position on the dial where this toothpick is. And finally, we're going to have a meter over here. Let's turn that on. And that's showing that the thermocouple, which is mounted right here on the heatsink fin, is attached to that meter, showing a temperature at the moment of 80.6 degrees Fahrenheit. And we'll keep our eye on that as the test proceeds. This is A1, 55 hertz. And turn up our power a little bit. See a little bit of motion down there now, 55 hertz. I wonder if there's a little flag there, might be buzzing a little bit. But let's go down to A0, which is 27.5. There's 27.5 hertz. Let's see if I can magnify that scale. And you see that little fluctuation that's caused between the beat between the frequency that the moving magnet motor is operating at and the frame rate of the video system on this particular iPad. Anyway, that's 27.5 hertz. That's A0. And our temperature is up to 85 degrees on the heatsink there, so not too bad. All right, let's go down now to A minus 1, 13.75 hertz. By the way, the acoustic output's starting to drop off right about 22. So, and it's gone pretty quiet by 16, 13 point. Close enough. Over here you can see, I think, the cone moving in there. This is 13.6 hertz right here, right now. And you can see we're getting pretty substantial excursions. Let's drop down now to A minus 2. Six point. 6.875 hertz. We're getting lots of motion in there, and we're getting close to full excursion at this frequency based on that scale. So let's go down one more octave to A minus 3, 3 point. We started to, what that knocking noise is, that we've reached the limits of travel. So 3.43. Okay. And that's about the maximum travel for the motor right there. And again, you can see the cone moving pretty good in there. It's pushing quite a bit of air right at the moment. And our temperature now is a little over 100 degrees, 102 degrees Fahrenheit on the south heat sink. This location right there. Anyway, for those of you who are keeping track, the diaphragm in this particular transducer prototype weighs 209 grams. The moving magnet assembly weighs 148 grams, plus we've added 50 grams with this steel clamping collar to balance out that heavier diaphragm. So 148, 198 now, plus 209, so we're just over 400 grams of moving mass. Our heat sinks, or rather our voice coils, weigh 148 grams, the combined. And for those of you who are keeping track, the spring constant of the diaphragm is 1/8 inch per pound. So it means that on that full excursion at 3.4 right here, we are actually providing 6 pounds of force in either direction to get the full excursion. So that's it. And we're up to 109 degrees, which that's noticeable, but it's not excessive. There's no smoke. Thank you.